All right, so the last part of the question, they're asking for the current on short circuit and also the power factor on short circuit. Now remember, when it's on short circuit, these external resistors are now removed from the circuit. So we only have the impedance of the rotor phase coils. Okay, so that if we look at one phase, it's only the Z of that coil. The external resistance is now shorted out of the circuit. All right, so let's see. So now there's something a little tricky here, and this is why I separated the video just to almost highlight this. So the Z of the rotor now is 0,2. So that was what they told us in the question. That was the resistance of the coil, 0,2. And we calculated what the inductive reactance of the coil is. Remember we used 2 pi FL to get what XL is. All right, and we got that as 12,57. Now, why have I multiplied this by 0,05? Okay, and that is actually 5%. All right, and why have I done that? They told us in the question, they said also calculate the current and the power factor when the slip rings are short circuited and the motor is running with a slip of 5%. All right, so the rotor is now moving at almost full speed. So the frequency of the rotating magnetic field of the stator, so let's look at the picture when you look at this. So the frequency of the rotating magnetic field of the stator is moving at 50 hertz, and the speed of the rotor is not, remember it's an induction motor, so it can't ever reach 50 hertz. It is running at 95% of this 50 hertz. All right, so it's almost there. It's 95% of the way there, but not 100% of the way there. So when we think of that, this induction motor or a induction motor, the only reason it can turn is because it's being cut by this magnetic field. So of the full 50 hertz or of 100% of this field, only 5% is now cutting this rotor. So I always give this example. I don't know if it's right to use this example, but if you got a car, two cars, and they're riding next to each other, the one car is riding at 100 kilometers per hour, and the other car is riding at 95 kilometers per hour. So think of this as the stator, this one going at 100 kilometers an hour, and the rotor is going at 95. So if I ask you, what is this car, the slower car, what is it experiencing relative to the faster car? So it's experiencing only 5 kilometers per hour. So it feels like it's moving 5 kilometers per hour faster than this car. So if you were standing still, like when the rotor is standing still, if a man is standing over here, let's just say a man is standing still over here, he is experiencing 100 kilometers per hour. That car is like flying past him at 100 kilometers per hour. But this car here, it's only going 5% faster. So it's slowly creeping forward, slowly faster. All right. So it's the same thing with the induction motor. The rotor is going 5% slower. So it's only experiencing 5% of the synchronous speed. All right. So that's why we multiply the inductive reactance by 5%. All right. And the reason why we don't multiply this the resistance by the 0,05 or the 5% is because it's a resistor. So the resistance doesn't, or I should say it's the resistive part of the coil, and that doesn't get affected by frequency. It's only the inductive reactive part that gets affected by the frequency. So that's why we multiply only that part, the XL, by the 5%, and then we get the total reactance, or sorry, the total impedance of the coil. Okay, so that's when it's at 5% slip. All right, so I wrote here, I highlighted it here. I said, why? Why is it? Because the frequency of the rotor relative to the synchronous speed is only 5%. The rotor experiences a frequency cut in the rotor bars of 5% of the synchro speed. Okay, so that's only the rotor bars only get 5% of the synchronous field. Okay, so that's the impedance of the coil of the rotor at 5% slip when the external resistors are shorted out. And over here now, the current, again, because the rotor is only experiencing 5% of the rotating magnetic field, it means that the EMF that is generated, or generated in the rotor, is only 5% of the synchronous speed. So that's why we multiply now even the voltage by the slip. So here we get 0.05 times 288.67 divided by the impedance we just calculated, and we get the new current. So that's the current at short circuit when the resistors are out of the circuit. And we can use the phase angle to calculate the power factor at short circuit as well. So I hope that makes sense. It's just these two parts here that are multiplied by the slip, and that's normally the confusing part. So I hope that makes some sense.